A rectified linear unit function. That looks like something you've probably never seen before, but it is not too difficult to unpack this. So this function is very simple, I would say. It takes the maximum of two terms, 0 or x. Maybe for the sake of precision, I'll write this. Okay, and it takes x as input. So what happens if I put 5? That's ReLU of 5. It's 5. Okay, what's ReLU of 2? It's 2, because 2 is greater than 0 and 5 is greater than 0. So what's ReLU of minus 7? This is going to be 0. And so will any negative number also will be equal to 0, because this is we're taking the maximum of 0 and the negative function. So in fact, I can write ReLU as follows. So ReLU of x will give me x if x is greater than or equal to 0. Actually, yeah, greater than or equal to 0. And it will give me 0 otherwise. Or maybe I'll write x smaller than 0. Well, smaller than or equal to 0 also. Yeah. Because if we take the limit from the left and the right at 0 of ReLU of x, we get 0 here and we get 0 there. So it's fine. It's nice. Okay. So that is good. And now we want to know if it's differentiable or not. Now, the idea here simply is to look at the limits from below and above, indeed. First thing I want to do before anything else is I want to graph this function, just to give you an idea. So it's equal to 0 and for any x that's less than or equal to 0. So I want you to imagine that this is exactly on the x-axis, but then afterwards it's very simple. It's just, you know, you could even call it y is equal to x and color it in green, because why not? Because this is effectively what's happening. Now, where is this function not differentiable? Is it differentiable nowhere? Well, that's not true, because at least for this part, we know this is a linear, it's literally a line, and it has a slope. So at this point, it's differentiable, it has slope of 1, that point as well, that point, and so on and so forth. So it's definitely not nowhere. It's definitely not finitely many points either, because if I choose, for example, here an interval from 0.5 to 1.5, forget about 1.5, just to infinity, you know, I'll get an infinite line. And this infinite line is differentiable everywhere. This specific line, this specific part of the function. So it's not, so it is differentiable on more than just finitely many points. Then we have everywhere or everywhere but x is equal to 0. Then, what is the difference here? What is the key factor? It is differentiability at x is equal to 0. Now, if you want to do it graphically, you can zoom in here, and you will see that here there is a sharp turn. So you're going like this, like this, like this, like this, and then it's like that. So there's no, for example, smoothness, like you go like this, and then it's like this, and then one time just change 45 degrees up. So it's a sharp turn, and sharp turns are not differentiable if you want to do it graphically. But if you want to do this problem in a more argumentative manner, we can take a look at the limit as x goes to 0. From the left and also from the right. The limit as x tends to 0 positive of ReLU x is 0 positive. But then the limit as x tends to 0 negative, ReLU of x is just equal to 0. So that is quite a problem. Not with ReLU of x, because this is not the problem actually. Actually, it is continuous because I can draw it without lifting the pen. But the problem is with the derivative. So the rate of change. So is the rate of change continuous? If the rate of change is continuous, then that would be nice. And if I take the derivative of x on its own, I indeed get 1. And I take the derivative of the below function, which is the constant 0 function, I get 0 because it's a constant, it's not changing. Then the graph for the limit for the derivatives, according to this, and this is actually true, so it is true that if we take the derivative, it will have this form. And then from the positive side, I get 1, because that's the rate of change. From the positive side, I'm on the line, and if I'm on the line, then my rate of change is 1, because this is the unit line. Now, if I'm on the 0 minus, then in that case, my rate of change is 0, because I'm on the constant line. And notice now that the color coding is very useful for the visual image. So, something here. So the rates of change are not continuous. If I were to draw the rates of change, it would be as follows. Now I want you to imagine that this is exactly on the x-axis. This is very badly drawn, but just trust me. And for the slope, this is, let's say, 1. Then we have this immediate jump from the red rate of change to the green rate of change. And that's why there's a discontinuity. It looks like the stair function, which is not continuous. So a function is differentiable at a point if its derivative is continuous, more or less. And because this is not the case, then it is not differentiable everywhere. So in that case, it will be differentiable everywhere, but at x is equal to 0.